Cool, cool, cool. So we started talking about abstract data structures 2 weeks ago. We're going to continue that discussion today. All right, this is displaying a little bit smaller than I would like. Let me see if I can change that. That looks better, doesn't it? Okay, so topic 5.1.11 is describing the features and characteristics of a dynamic data structure. So we need to understand this major difference between static and dynamic. Static is staying the same. A two-dimensional array, typically an array, does not change size. Remember that there's a difference between a Python list and an array. A Python list can change size, but an array and a lot of other programming languages, you have to state what the size is, and that size stays the same for the entire time that it's being used. So that's a static data structure. A dynamic data structure, like a stack, a queue, a linked list, or a binary tree, changes size over the course of it being used. You can add items to a stack. You can reduce items from a stack. You can do the same thing with a queue and do the same thing with a linked list, which is what we're going to be focused on today. So in general, when we talk about the characteristics of these types of data structures, a static data structure, you determine the size or length at creation. It may or may not be good use of memory space, a static data structure, depending on how big or small you're making it. And typically, with static data structures, we use for loops. Because the size is static, then we can say, go through 25 times, go through 1,000 times. And we know how many times it's gonna loop through. With a dynamic data structure, the size or length is determined by what the contents are of that data structure. It is usually a good use of memory space. I'm skipping this one for now because we haven't talked about those in detail. But it is a good use of memory space because it will dynamically size according to how much data you have in there. You will not have a stack that is 1,000 items long if you don't actually have 1,000 items to hold in that stack. If you only have 10 items in the stack, then the stack is only 10 items long. So it uses only the memory that is necessary. Typically, although not always, we use stacks and queues and linked lists with while loops because the size of the thing can change, and therefore a while loop is a better fit. So in case you ever wondered why we use for and why we use while, this is one of the decisions. So, nodes and pointers. Everything in here is a node. You can think of a node as a piece of data encapsulated by something that is going to allow us to access it. So you can also think of a node as a location, like a location on a map. The location on the map not only has information, like if you're looking at a map and you're looking at Cleveland, you not only have the information about Cleveland there, you also have roads that will take you there, and you have roads that will lead you away from it. So the analogy of a node being like a location on a map helps us to understand how pointers work. Pointers are pieces of information, addresses in memory that allow us to then say, okay, there's a node over here. So this pointer right here actually contains the address in memory of this node. And this pointer contains the address in memory of this node. And this pointer right here contains the address in memory of this node. So that once we have started looking at this node, we can find every other node in this, what is called linked list. Another way of visualizing this is through having these, squares where we have the piece of data itself. Because without data, then having a data structure is meaningless. We have to have some information. And this is what is called a doubly linked list, because there is a pointer here that shows us where the next node is. And there's also a pointer here that tells us where the previous node is. So this is called a doubly linked list, and we'll get into more details about it, because every node has two pointers, one to point us to the next node and one to point us to the previous node. Any questions about these two terms, nodes and pointers, right now? So a node is, let's say, an object that contains at least two pieces of information. It contains the data, because this is a data structure, there needs to be some data. That data could be a string, it could be an integer, it could be a list itself, it could be a picture, it could be anything. So the node contains data, and it contains one or more pointers to other nodes. So again, you can think of a node as an object that contains data and one or more pointers. Does that help? So I'm having trouble reading that question, Ayana. The nodes, the pointers direct the nodes. Is that what you meant to say? So the pointers direct to other nodes. So those pointers are always pointing to other nodes, and they point because they contain the address in memory of those other nodes. Does that help? Did I answer that? Okay. So there are three pieces of vocabulary that you need to be familiar with when talking about a node. There's the head, the data, and the tail. I am not concerned that you define these in these particular ways. Really, what I want you focused on is the data and the tail. In any sort of linked list, you're going to have data. In any linked list, you're going to have a tail, and that tail is going to point to the next node. If there is no next node, you see that this is represented in this particular diagram with these three horizontal lines. It's just going to be null, all right? You've seen null before. Null means nothing, right? And so there will be no pointer here. If this is null, then you as a programmer know that you're at the end of the list. Head can change depending on the linked list that we're looking at, so that's why I'm not so concerned about the head yet. But every node does have a data and a tail. And that tail is simply the pointer to the next node. So the next section is all about how linked lists actually operate, all right? So now that we've talked about pointers and nodes, let's take a step back and talk about what the linked list actually is. So let's break this definition down. A linked list is a linear collection of self-referential structures called nodes connected by pointer links. So Linear means in a line, sequentially, one after the other. Self-referential structures, meaning that they have addresses to themselves. And that's where we get into that head piece where the head actually points to the data. But again, I'm not worried about that piece right now. What I want to focus on most is the concept of a node and that they're connected by these pointers that are links. In order to have a linked list, you have to have somewhere a pointer to the first node of the list. So you have to have an address that you keep in a variable somewhere so that you know where the list starts. If you lose that address to the first node of the linked list, then you have lost the entire linked list. There's no way you can get it back because there's no way you can look through memory and go, oh, here's where it is. So this trips a lot of people up when they're programming because they forget to keep that pointer. And again, this is defined differently than it was on our previous slide where we talked about head. This is the definition that I really want to use for head, which is that we say that this variable that I just talked about is typically called the head. You have to keep that head pointer somewhere, otherwise you lose the entire linked list. So every node that comes off of the linked list is accessed by a pointer member in the tail that is stored in each node. The pointer itself in a node is an address in memory, and so that address in memory is just a number. You can lose that number, the head, if you erase the variable or you overwrite that variable with something else. Does that answer your question? Yes, Ayana. So the numbers in the head, which isn't shown in this diagram, is that number in the head is the pointer that leads us to the first node. We're going to see other diagrams that help to clarify this a little bit. Like this one. So here's our head node, or our head pointer rather. And this head pointer is pointing to the first node. This is a linear linked list. The first one takes us to the second one takes us to the third one to the fourth one to the fifth one to the sixth one, and the sixth one has a null tail pointer, meaning it stops there. This is called a null terminated linked list, aka a linear linked list. All right, so we have this head pointer that gets us into the linked list, and the only way we can what's called traverse or move through this linked list is by starting at the beginning and going through the whole thing. So there are some advantages and disadvantages to this. If we want to use the data because maybe we want to search data for something and it's sorted, then it makes sense to use a null terminated linked list, because if it's sorted, then we know, all right, we need to go like, let's go through each one, and we know if we've reached this node, then we can stop. Now, a circular linked list, it's the same exact thing except for one difference, and this difference is actually pretty big, is that the last node takes us back to the first one. A circular linked list is helpful if we have nodes that we're adding in as we go through, and we want to keep searching the information, and we know that we're going to have new information come in, and so we want to be able to search that dynamic list without stepping out to the first one again. There are a variety of different applications as we get into this that you are going to see that you can use for circular linked lists. Generally, they make it easier as the programmer to, you just keep track of where you are in the linked list, and you don't have to worry about having, always using that head pointer, but you always need to hold on to it because otherwise you could lose your linked list. But circular linked lists can be used for more dynamic data structures. You use loops, while loops, and for loops to navigate through linked lists. You would use a while loop typically for linked lists. You would say, for example, for this null terminated linked list, you would say while tail is not equal to null, and that would allow you to go through the whole linked list, and it would stop here. For the circular linked list, presumably we would be looking for something in that linked list. So maybe while data is less than 5 or something. And you would keep going as long as data is less than 5. And maybe data is always less than 5. But while we're in this loop, we're adding more data. And once it hits 7 or something, it'll stop. So it all depends on the application of your linked list. So there's a couple of operations that we need to be able to understand how to do on linked lists. I made mention in the circular linked list that we would want to insert members into the linked list. So there are 3 kinds of insertions that we might do. The first kind of insertion is inserting a node into the very beginning. If you insert a node at the very beginning of the list, what do you think you would have to do? What would have to change? Which variable would have to change? You're right, which variable would have to change? Which pointer? There's a very specific pointer that would have to change. Yep. And what do we call that first pointer? Yeah, awesome. The head pointer. So we can also insert a new node at the very end of the list, and this is only happens if we have a null terminated, a linear linked list. If you have a circular linked list, there is no end. And then inserting a new node in the middle of the list it's kind of fun. So this one shows what happens when you insert into the middle of the list, where you take the tail pointer and you point it to your new node. And wherever that tail pointer was pointing, you make the tail of the new node point to wherever the previous one was pointing. And so you just kind of go, no, let's point here, point there, and it's been inserted. When the list is empty, when the head is equal to null, the insertion is really easy. The head will simply point to this node that you just created. Now, there's another definition of tail that I don't want you to get confused. There are some data structures where you use tail to point to the last node in the list. And that can get confusing because we just define tail as being a part of a node. But some implementations of linked list, they include a head and a tail pointer so that you have a pointer to the beginning of the list and you have a pointer to the end of the list. So you will see a lot of diagrams that include both the head and the tail. So if we're inserting at the beginning, what we do is we take this head and we point the head towards the new node, and wherever the head was pointing before, we make the new node now point to that node. So we see here that this head is pointing to the new node, and this new node is now pointing to the previous first node in the list. We're starting to see multiple definitions for head and tail, and I know this part can get confusing. So we have a head pointer that's pointing to the head node, and we have a tail pointer that's pointing to the tail node. And every node has a tail that points to the next node. I don't know why people who kind of invented these data structures couldn't come up with different fun names for things. But as long as you are able to read these diagrams, then you'll be all set. We will have a practice, we'll get our practice in by doing a project about linked lists, so you'll understand how linked lists work. Now, if we want to insert something at the end, it is roughly as easy as inserting something at the beginning, where this tail pointer is now going to point towards this new node, right here. And what was the last node is now going to point towards the new node instead of just pointing to null. All right. I see that I might have cut out. I see that I might have cut out there for a minute. So what we're going to do is we're going to update the tail to point towards the last node, and the previous last node is now going to point towards the last node. These diagrams probably explain it much better than we can do in words, but in general, what we're doing is we're putting it at the end by changing where the last node points and where the tail pointer points. Now, here's insertion in the middle. I liked our other diagram a little bit better for inserting in the middle, but if that one didn't work for you, then I see your question, Zainab. We'll get to that in a second. If that other diagram didn't work well for you, then this one should hopefully clarify it. Where this node is currently, this node that contains -1 is pointing to the one that contains 16. What we want to do is we want to change where this one is pointing. This one will now point towards the new node, and the new node will point towards this guy. So in code, we will actually have, so this shows us, unfortunately, the Java code later on, but I'll explain what the difference would be between the Java code and the Python code. It's actually pretty minor. But in code, in the object, in the node object, you'll actually have a member variable that contains the address of the next node. So it'll actually be changing all sorts of variables, changing the variable on this object, changing the variable on this object, and then you're done. This does pop up a website for us. I recommend keeping this website on hand. It does a really good job explaining. Wait for it to load here. It does a good job explaining these functions on singly linked lists using the same diagrams we just saw. So it's a good reference to keep on hand, like I said. And it does include these code snippets. Again, this is Java. Please ignore the C++. There's a lot of notations in here that you're unfamiliar with, and it won't actually be helpful for you right now. So if we're adding a node, if we're adding a last node, so adding to the tail, what we see here is if for some reason the new node that we're trying to add is null, meaning you didn't try to add one, then be like, get out of here, return. You're not even trying to add anything. Why are you calling this function? It's just checking to make sure you're not trying to add a null node. All right, as long as the node you're adding has some data in it, it is a node. Because we're adding it to the end, we're going to take the next member variable and set that to null. Remember, we're null terminating this linked list. So the next will automatically be set to null. We have a head pointer as a variable. If that head pointer is null, that means there are no nodes in the linked list right now. So that means we are adding this to the linked list, and it's the only member of the linked list. So the head pointer and the tail pointer will be set to this new node. In the case that there are members of the linked list right now, that's where this else comes into play, then we are going to set the member that the tail points to this new node. I'll wait to make sure I'm stable again. All right, I think I'm back with you. So we're taking the last node, the current last node, and we're saying, hey, instead of being null, you're going to point to the new node. And instead of the tail pointer pointing to what it previously pointed to, point it to this new node. So we're bumping it on to the end. If this code isn't making sense to you, if it's kind of murky, we're gonna be doing essentially this. We're gonna be implementing add list, add first, and insert after in Python. So you'll have a good idea about how to do this. I'm not gonna ask you to make your own nodes. I'm not gonna ask you to make those objects. I'll be making those objects for you and asking you to do the add last, add first, and insert after. So for add first, again, if the user called this function and there's nothing there, then just return, get out of here. If not, if we're adding to the beginning and the head pointer is currently not pointing to anything, that means that we don't have a linked list yet, and we need to make it. So again, we want to make our new node. We're going to null terminate that new node because that's the only one in the list. So we're going to put that null as the pointer for the next one because there's no next one. We're going to have the head and the tail point to this new node because there's only one node. If there's already a list in there, then we are going to say, okay, so our new node, the next pointer, the next one, should point to what's currently the head. And then let's change our head pointer to be that new node. So now the head will point to this new node. Finally, the insertion in the middle, we need to know what we're inserting it after, and we need our new node. So in this case, if we have an actual node that we're inserting, if that previous node is null, then that means we're just adding a first node. If that previous node is the tail, then we're doing the same thing as adding last. So these two are taking shortcuts and saying, you don't have to do this all over again. We did this up here in add first, and we did this up here in add last. Finally, if we're actually inserting a node in the middle of other nodes, then what we're going to do is we are going to make a new node called next. We have to do this as a temporary thing. And that is going to be set to wherever that previous node was previously pointing. All right, we're going to hold that in memory. We're going to need that in a minute. We're going to take that previous node and we're going to point it towards our new one. And then we're going to take that new one and point it towards the next node. All right, that one that we kept in memory. And so we're just kind of holding on to that information. We're putting the new one in, and then we're saying, hey, new one, point to this one that we held in memory. This can be very difficult to visualize from the code. And honestly, in Python, it's going to look very similar to the Java. But when you actually go through it and you implement it step by step, that's when you'll get a good understanding of how this works. Any questions? Again, I don't expect you to understand it completely from the code, but hopefully you can use this as a resource, and this will help you when you actually get to the project. All right, make sure you save that link because it's about to go away. I can always send it to you later as well. Can I move on? Okay, awesome. So it's important, obviously, throughout our entire study of computer science to be able to plan things, to be able to sketch things, write things out. So when you sketch a linked list, always make sure that you have the data and you have a pointer. All right? Using rectangles makes it easy. Using arrows demonstrates the pointer. That is universally recognized. Having an arrow is universally recognized as a pointer. Pointers work in one direction only, and that should make sense at this point because it contains an address. So it only logically makes sense that it works in one direction. You can write null, or you can write X. I apologize for being distracted. Someone is filling my Instacart order that we've been waiting for a while. So I'm sure you understand the urgency of groceries. Okay. So make sure that when you're doing linear lists, that you are making sure that it is going in one direction and demonstrating that one direction. And I did make mention that this null can just be an X, okay? All right, this is new. Doubly linked list. Ooh. I feel like I should have sound effects. So you have a head and a tail. This is also called a header and a trailer. Yay, more vocab. In a doubly linked list, It's a header and a trailer because you can think of this in two ways. You can think of this going in this direction. You can think a doubly linked list of going in this direction. Every node has two pointers, all right? It has a pointer pointing to the next, and it has a pointer pointing to the previous node. So you can traverse or go through a doubly linked list in two directions. And in fact, from any particular node, you can move in either direction, depending on how you are using your data. So at this point, I want you to think back to the text monster game. To remind you of the text monster game, it was where you had like 3 floors and 5 rooms in each floor. And from each room, you could move from room to room to room, right? And so we did that using a list. But think about using a linked list for that now. Think about using a doubly linked list. So that from this room, this is on the left-hand side of the whole floor. From this room, if there's no more left, then it just has a null pointer. And we know that there's nowhere we can go from the left, and so we can tell the user that. We don't have to say, oh, is this 0? Is this room 0? No, we just go, all right, is the previous node a null pointer? Is the previous link a null pointer? If it is, we can't go to the left. And from every room, you have a pointer to go right and left. Now, you could have other information, the data about it. Is there a monster in this room? Well, that's part of the data, right? That's other pieces of information in the object. So you could completely redo the whole text monster project using doubly linked lists. What? Okay. We did talk about circular linked lists. You do have to designate in your circular linked list which one is going to be the header, which one is going to be the head pointer or the head node. And your head pointer is going to point to that header. Again, there's one pointer for each element. It's not doubly linked. You can make a circular doubly linked list if you want to. I'll repeat that because it looks like I might have cut out. You can make a circular doubly linked list if you want to. But the important part here is that the last node links back to the first or the header. In summary, we have 3 that we talked about, 3 types of linked lists. We have our singly linked lists, our singly circular linked lists, and our doubly linked lists. I did say that you could have a doubly circular linked list where this next points to the beginning and this previous points to the last. But there are not very many applications for that. So we're mostly focused on these types of linked lists. This is the end of this lecture. What questions do you have about linked lists? Ooh, yes, doubly. It's a fun word too. What else? Exercises, yes, you'll absolutely see linked lists on exercises. We did not talk about the exercises that were due yesterday, or due yesterday as due dates are weird now. But yeah, you will definitely need to understand how to sketch a linked list, how to implement a linked list in pseudocode. We're mostly going to be focused on Python first. It's easier once you understand how to do it on Python, because then you can translate that to pseudocode. other questions about linked lists? Other questions about the projects you're working on? Zainab, you were working on Fibonacci yesterday. It's a tough one, all right? So we have a couple minutes. Why don't we take a quick look at that, at Fibonacci? So let me get on Replit real quick. Okay, so let me help you. And this is how I want you to start off your function. The function should take one argument. In this case, we're calling that sequence, because we want to find the 20th digit or the 10th digit or the 30th digit in the sequence. Your function should do several things. One of those things that it should do is if we're looking for let me say it this way. If we're looking for the first number in the sequence, what does that equal to? What is the first number in the Fibonacci sequence equal to? Yeah, it's equal to 0. So it's equal to 0, just return 0. So if sequence is 1, Instacart, I'm telling you, getting groceries is talking to my shopper, chatting with my shopper. I have a personal shopper. I feel so bougie. Okay, so if it's equal to 0, return 0. Okay, now I'm sorry, it's equal to 0. If we're looking for the first number, so if sequence equals 1, return 0, right? The reason we have to do that is that we have to at some point have a definition for the sequence. We have to say what it starts at and then what is going to increment it. Now, Fibonacci sequences can start, the first two numbers can change based on how you want to run your sequence. The typical Fibonacci sequence, it goes 0 to 1 to 1, because 1 plus 0 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 5, 5 plus 3 is 8, and so on and so forth, right? You can also have Fibonacci sequences where that second number in the sequence is totally different. You can go any direction you want to, but after that point, everything is defined. So 0 plus 3 is 3. 3 plus 3 is 6, 6 plus 3 is 9, 9 plus 6 is 15, 15 plus 9 is 24, 24 plus 15 is 39. You see how it's totally different based on those first two numbers. So because of those first two numbers, we have to define those first two numbers in our find Fibonacci function. So if we're looking for the second number in the sequence, what is that going to be in our standard Fibonacci sequence right here? what is the second number in the sequence going to be? Yep. It's equal to 1. So we're going to return 1 if we're looking for the second number in the sequence. That's the easy part. I admit that's the easy part. Hard part is what to do if we're looking for anything else other than the first or second number in the sequence. This is math. How do we determine the fifth number in the sequence mathematically? What are we adding together? In terms of n, what are we adding together? So, not the number plus 1. So in order to determine the fifth number in the sequence, what two numbers do we add together? Not the first and second. That would give us 1. How do we get 3? What two numbers are we adding together to get 3? In other words, we're adding together the fourth and the third numbers in the sequence. So if n equals 5, we're adding together the fourth plus the third number in the sequence. If n equals 8, we're adding together the seventh plus the sixth number in the sequence. So to determine n number in the sequence, we need to add together the n minus 1 number in the sequence added to the n minus 2 number in the sequence. That's where the recursion comes in. That's where the magic of this function is. Once you figure out how you're going to do that, it's seriously, it's one line of code, but it can be difficult to arrive at that. I've got my next class starting up in a minute, but that's what you should be thinking about for tomorrow as you're working on the Fibonacci, as you're working on this. Any final questions? N is a variable. In this case, what is the number in the sequence? What variable holds the number of the sequence in this case? It's sequence. Oh, don't leave, don't leave. We'll start physics. We're going to start physics in a couple seconds here. So the variable is sequence. Okay? I'll see you guys tomorrow. My computer science class, physics, we're going to get started here in just a second.